afternoon, everyone. Thank you for having me at this great conference. It's my first time here. It's actually my first time in Calgary, so I've been checking everything out. I'm actually based in Los Angeles, California, where it's very warm, and so I fortunately checked the weather before I left and brought a jacket, because it's a little bit chilly here. But I'm going to be talking today about what I believe is the future of flight, which is hydrogen electric propulsion systems for aircraft. And in terms of my background, I spent the majority of my career working for NASA, specifically the robotic space program at NASA's Jet Propulsion Laboratory, and I always did things which were not on planet Earth, quite literally. My PhD is in propulsion systems enabling exploration of deep space, like out to the main asteroid belt, and I also have an expertise in entry, descent, and landing systems for landing on Mars. I worked on the Curiosity rover, and then re-entering Earth's atmosphere, and I even had a stint working on developing a facility for the International Space Station to explore the nature of matter in a quantum mechanical way. And one of the things that I really learned from working in the space program for the majority of my career is that you can solve really challenging problems if you're imaginative, you have the right training, and you have the right team. But after being in a space program for almost 20 years, I decided it was time for me to do something which is a little bit closer or down to earth in terms of being able to solve challenges here at home. And I truly believe, as probably all of us do in this room, that climate change, CO2 emissions, is probably the challenge of our species, of our generation as citizens of planet Earth, not just for human society, but for all of the creatures who live here. So I actually left NASA and I went to work in green transportation. I actually went to work on the development of the Hyperloop, which is a ground transportation system which is kind of like a spacecraft traveling on the ground, operating off of grid electricity, allowing it to be carbon neutral and going really fast. I then spent about 2 years working on the development of battery-powered aircraft for electric vertical takeoff and landing applications, and both the Hyperloop and the eVTOL space that I worked in showed that actually batteries are not a good solution for heavy-duty transportation systems, whether that is buses, trucks, trains, the Hyperloop, or aviation. And so in late 2019, I was deciding that I really need to do something to address the decarbonization of aviation by coming up with an energy storage system which could give you the same range, the same payload, the same endurance as you would get with an internal combustion engine. And the way to do that, I believe, and as I'll present to you today, is with hydrogen. So the name of my company is Hydroplane, which I founded, and I am also the CEO of it. But in terms of stepping back a little bit, in terms of my background, is I'm actually a huge fan of science fiction. Anybody in the audience a fan of science fiction by a show of hands? Okay, a decent amount. Usually that's the case at energy conferences and aerospace conferences. And ever since I was the age of 6, I would watch Star Trek, actually with my dad, original series reruns, as well as Next Generation, which was coming out in the 1980s when I grew up. And I've always been fascinated by the ability to explore space, the ability to potentially find alien civilizations within our galaxy, and obviously that's where Star Trek comes in. And what I think is so amazing is that the engineer actually can make science fiction science fact. So with the discipline training of science and math, applying it to technology, you can literally build the future that you imagine and how you want it to be, which is very much in line with kind of like the Star Trek mentality. And this, of course, is a genre of science fiction which is known as utopian science fiction. But of course, science fiction fan knows there's also dystopian science fiction, which is a very different universe, a very different world from the world of Star Trek. And an example here, of course, by this graphic is from Blade Runner 2049. I actually like the original Blade Runner better, but still, it was a good movie, regardless, 2049. And what happened, of course, in this vision of the future is climate change has run amok, and the city of Los Angeles has been ravaged by poor air quality. Pretty much all life forms other than human beings are no longer in existence. And what we can see is that we have to think about the environmental cost. And so all of us in this room are disruptors in our own sectors, and it's our responsibility as well as an opportunity to create technologies to reduce our carbon footprint. And so that's what I'm doing now in the context of my own company, and I think that's probably what everybody in the room is interested to do in their respective areas. But I do take it back to rocket science, because that is my training. All of my degrees are in aerospace engineering, and I have a actual expertise in propulsion systems, and so I actually had the opportunity to get interviewed by William Shatner, and I told him Star Trek really inspired me to become an engineer, and he'd heard that all before. And so what is important is that the space program is both inspiring, and it can inspire other people, and it can create a whole new generation of scientists and engineers, such as myself and other students that I teach, that are really interested in doing the impossible. So now when we talk about what the challenge is in the context of aviation, is that the carbon footprint of aviation, the amount of CO2 coming out of the sector, is actually increasing. It's on the rise. And although it only represents about 2% of the total anthropogenic CO2 emissions from human society, it is going up relative to other types of emissions because aviation is so difficult to decarbonize. So with ground-based transportation, you can have batteries in passenger cars, you can have rail systems, whether that be metro or high-speed rail, running off of a grid, which is based off of renewable electricity. But aviation is just continuing to increase. More aircraft are being built. More people around the world are starting to use that as a form of transport. And then the other challenge with aviation is it's a highly regulated field, which means that if you're going to develop a new aircraft or a new type of propulsion system, it's going to take you several years to get it into the marketplace, to get it into existence. And if you go back up and look at the net zero display over there behind us, there's actually a section which talks about in 2040s, I'll be getting on my hydrogen aircraft, right? Well, I'll challenge that assumption because I think we're going to have hydrogen aircraft much sooner than that, before the end of this decade. But in terms of large jet aircraft, it probably is going to be the 2040 timeframe. But you can really see how the challenge is now to decarbonize aviation, and because of the complexity of getting it into the sector, fully certified, fully regulated, we've got to start working on it now. And I love to always go back to my space program stuff because this graphic is incredibly important. This shows the terrestrial planets, with Earth, our beautiful planet, in the middle, Venus, the red one on the left-hand side, which is one planet in towards the sun from us, and then Mars, which is one planet out from the sun. And what happened to Venus is that it originally started off like an Earth-like planet, but over the course of the past several billion years, it has experienced planetary-level climate change. It experienced runaway greenhouse gas effect, where CO2 in the oceans boiled, which then created a really, really hot environment. And right now, on the surface of Venus, the surface temperature is 470 degrees centigrade and 100 atmospheres of pressure. So as we know it, that terrible runaway greenhouse gas effect has basically terminated any possibility for life on the surface, if there ever was. Mars is a very different situation, where it experienced some kind of event, perhaps with the collision of an asteroidal body, which ended up shattering its core, which then disrupted its magnetic field, which then allowed in-space radiation to rip off its atmosphere, and Mars is very cold, has very thin atmosphere of primarily CO2. So we can see with our own terrestrial neighboring planets that climate change can affect a planet at that level, to the point where all life, or the potential for life, can be destroyed. So it is a really important thing that we need to deal with going forward. But when we talk about how do we decarbonize aviation, we need to shift over to electric propulsion. Just like we have electric vehicles with our cars, we can have electric airplanes. But unfortunately, because aircraft are really sensitive to weight, it can't be with batteries, because batteries are too heavy. But it can be with hydrogen electric propulsion, which utilizes hydrogen fuel cell technology. So in addition to being carbon emission free, a fuel cell only puts out water, it also has the ability to be much lower noise. Those of you in the room who drive an electric car know that it makes very little noise compared to the combustion engine equivalent system. And it has the ability to have significantly lower maintenance costs, because you no longer have oil changes, you no longer have these wear and failure degradation modes which are associated with the combustion process. And when that translates economically to an aircraft owner and operator, lower maintenance costs means lower operations costs. And it also has the potential to give you lower fuel costs, because if the price of hydrogen is driven by the price of electricity, now all of a sudden you have significantly lower fuel costs. So hydrogen electric aviation is actually an economic win-win, in addition to being carbon emission free. So I wanted you to take that away and understand it. And then the other aspect, of course, of electrification of propulsion systems is that at the end of the day, we want to get rid of our reliance on non-renewable resources. And batteries still use lithium, which is not a renewable resource. But what is the most abundant element in the universe? It's hydrogen. It's in space, it powers our sun, and it exists in a chemically bonded form on the surface of our planet in form of water, or H2O. So being able to use hydrogen for propulsion, for electric propulsion, allows you to actually have access to a renewable resource. And that's why it's a really powerful argument for why we would like to use hydrogen as an energy carrier. And how do you make hydrogen? Well, you've probably all heard about there are different types of hydrogen. There's gray hydrogen, which can be reformed from hydrocarbons can be reformed to produce hydrogen, and that's called gray. You can capture the carbon emissions in that process, and then that would be called blue hydrogen. The real goal for the hydrogen economy is to shift over to green hydrogen which is produced via the electrolysis of water using green energy. And in case you didn't know it, the word hydrogen actually means water genesis in Greek, the coming together of hydrogen and oxygen to produce water. So that's kind of an interesting aside. But ultimately, electrolysis using green energy to produce hydrogen allows you to create green hydrogen, which can be used for a range of different use cases. But if I talk a little bit about the engineering or the science behind why green hydrogen is so advantageous as a fuel, the reason is because of its energy density. It has a factor of 10 improvement in specific energy over lithium-ion batteries, and it has a factor of 3 improvement over hydrocarbons when it's combusted. When you do an electrochemical process with a fuel cell, it's even more efficient than the traditional internal combustion engine process. So what is used as the best rocket fuel of choice for launch vehicles? Liquid hydrogen and liquid oxygen because of the high energy density. So it makes sense to use it for the aviation application as well. The other benefit, of course, is that you can produce it from renewable electricity and you can produce it locally, which takes away any limitations you might have by having access to oil coming from a foreign country. So locally produced and therefore locally used, which also further reduces the carbon footprint of transporting the molecule from point A to point B. So many advantages in addition to being carbon emission free. And in terms of how the hydrogen fuel cell technology actually works, it's a pretty simple, passive, low temperature or room temperature system. So you bring in hydrogen gas, which is an H2 molecule. It enters the anode where it sees a catalyst, which is a reactive material, which makes the hydrogen gas split up into electrons and hydrogen ions. The electrons that are released is your source of electricity. The ions pass through something called a polymer membrane, in the type of fuel cell that we're dealing with, and then they recombine with oxygen from the air on the other side to produce the exhaust product, which is water. It is an incredibly elegant, simple solution to generating electricity in a very clean way. There are, of course, ways to further optimize this device, which is what we're working on as a company with a custom hydrogen fuel cell stack for aviation, but there are also ways to reduce waste associated with the production of these systems by reusing components inside of them from a mission to another mission, so after a certain period of time. Because it's a low temperature device, it likely will have a longer time between overhaul, which means that you can use your existing power plant for longer than you would for an internal combustion engine system, which also reduces waste from a basically replacement perspective. So in terms of what we're doing as a company, is we're developing a hydrogen fuel cell power plant for aviation. But one of the things that the space program taught me is that you don't go off and land the world's most sophisticated rover on the surface of Mars without having ever done it before. You actually work up in your capability in terms of mass, in terms of complexity, so that you can get to better and better missions downstream. So for reference, the space program, the Mars exploration program has been going on since the 1970s, but we've been able to perfect our landing techniques over the course of time by doing this incremental approach to get us to where we are today, which is landing really big payloads and ultimately people next. So you can do the same thing with aviation. So if you start with smaller aircraft and get those into production, get those into use, you can actually get the technology into the marketplace. You can drive demand, another end use for hydrogen, which drives more green electricity production, and you can get people flying for a range of use cases, which can include things like general aviation, flight training, vertical lift, urban air mobility, air taxis, cargo transport, and even low-capacity regional transport. And our company is actually funded by the United States Air Force as part of the Agility Prime program, because there's a whole range of use cases in the humanitarian aid disaster relief front, which already use smaller platforms. So you don't have to solve the jet aircraft problem first. You can solve all these other aviation use cases first and use that to advance the technology into these larger platforms in future. So who is our team? So we are a team of several of us are rocket scientists. We work for NASA on the development of launch vehicles. We work for Boeing on launch vehicles. We work for Blue Origin. We work for SpaceX. But we also worked on electric aviation at Boeing. And we also work in a variety of different electric vehicle automotive companies, because it really does take that combining of skill sets across these different sectors to be able to bring about this new product, this new technology into the aviation marketplace. And we're also have a company who have tons and tons of interns. So this is a huge opportunity for universities to have a whole new training program in the area of hydrogen electric propulsion systems, which is chemical engineers, material scientists, mechanical engineers, aerospace engineers, electrical engineers. It's kind of exciting how this is a tremendous opportunity across the board when you think about this new space. And our product is a 200 kilowatt power plant, which can fit inside existing single engine aircraft. That's our first implementation. And so our design requirement, of course, per the talk on the very first day of the conference, is that you have to match the utility and you have to match the cost of the incumbent, which is what we do. So our system, as designed, provides the same endurance, provides the same payload capacity, and fits within the limitations of a suite of aircraft that are at this 200 kilowatt power point. And that way, we can promote adoption. That way, we can get the product into the marketplace. And that way, we can get people flying emission-free. And the real challenge behind hydrogen propulsion is how you store the hydrogen, because naturally it's standard temperature and pressure. It is a low density gas, so you have to either store it as a high pressure gas, which is how it's done for the automotive application. I actually drive a hydrogen fuel cell car myself, because we have hydrogen infrastructure in California, or it has to be stored in liquid form for the aviation application to give you the range and the payload that you're looking for. And just to go a little bit deeper into how one optimizes this technology, we're a company of engineers, so we're always looking for sensitivities in the system. And whenever you're designing a new power plant for any transportation use case, you have to look at the combination of cost, unit cost, cost of ownership, the combination of weight, how do I make this thing weigh as little as possible, which maximizes payload capacity, and then durability. And durability is key to the aviation use case, because nothing requires higher reliability and safety than an aircraft does. So you have to focus on design for durability, which leads to reliability, which leads actually to a reduction in weight because you're operating more efficiently, which also can lead to a reduction in cost because you're operating more efficiently at the end of the day. And so we do that through a suite of new technologies, from a new membrane to new catalyst material, as well as a lightweighted design of our stack and balance of plant components, which ultimately gives us better specific energy, electrochemical efficiency. And so right around the corner, we have our first flight demonstration. It's part of our Air Force contract, and we call our first aircraft Protium, which is a single-engine aircraft that you saw there. I myself am a commercial pilot, but I will not be the first one flying it, because my investors don't want me to, but I'll probably be the third person that's flying it. And so we'll be flying in early 2023 outside in Los Angeles, in the desert location where we're based. We may also fly out of Edwards Air Force Base, who's our end-use operational customer. And it will be a demonstration of our technology, which will get this into the marketplace as quickly as possible. And in terms of what the future holds, this is the first implementation. This is the crawling before walking before running. But ultimately, we want to get this into rotorcraft platforms, which have tremendous use cases in humanitarian aid and disaster relief. We do want to get a different generation of the system into turboprop aircraft, which would require, we believe, a different membrane, which can operate at slightly higher temperatures to allow it to be more energy efficient. Whether or not it can be used in jet aircraft is a trade that we will do downstream, but it's certainly not our near-term focus. But we do also have a space program focus, which is robotic space exploration. And for those of you who don't know, hydrogen fuel cells, the PEM technology, was actually developed for the Apollo program and the Space Shuttle program. So it does have heritage at that point. So we'd like to get this into the human space exploration program at the end of the day. And I love to show a picture of Mars, because that is one of my main areas of research as an academic. I'm also a professor that I work on. But I do believe that the future of decarbonized aviation is hydrogen, probably hydrogen electric for these types of platforms up to turboprops, and maybe shifting over to hydrogen combustion for jet aircraft in future. And if you're interested in following us and what we do at the company, please do Hydroplane Aero. And if you're interested in following me and my shenanigans, I'm at Dr. Astro. But thank you so much for your time, and have a great rest of your conference.